Okay, so we're going to be doing a couple of practice problems on this video, and once again, I don't know from the video quality if you guys are going to be able to read my handwriting up here on the board, so I'll have to walk through all of this as well. I need to set my timer here so I know to stay under 10 minutes. All right, so here's what we got. We got a 1.5 kilogram object placed on a spring that has a spring constant of 30 newtons per meter. The mass is then lowered to its equilibrium position. All right, so we're wanting to find the stretch distance of the spring. We want to find the gravitational potential energy of the Earth's spring system before we lower it down to its equilibrium position. And then we want to find the energy stored in the spring at the lowest position when it's in equilibrium. And then what we're going to find is these two are not equal, and we want to be able to explain why. All right, so finding the stretch distance. Since this is in equilibrium and it's not moving anywhere, we can go back to do something that we have done a long time ago, and we can draw a free body diagram. So we have force gravity and we have force spring that is pointing up. So we know that these two are equal and opposite. So force spring is equal to force gravity. Now we also know that the spring force equation is force spring equals kx. We're going to drop the negative, but remember, force gravity is down. We talked about that in the last video, that force gravity is down, the spring force is up, so that's what the negative is there for on the actual equation. So since force spring is equal to kx, force spring is equal to kx, and we know that force spring is also equal to force gravity, so mg is equal to kx, and we can solve for the stretch distance of a spring. Okay, so once again, we're starting with our unstrained, we lower it down to its equilibrium position. Since this is an ideal spring, we have to understand in this problem here, we are physically lowering it down, because if we drop it from this position, it is going to oscillate back and forth, which is what the next topic is going to be. Okay, and we're going to get into that problem here in just a little bit. All right, so let's fill this in. So we have 1.5 times 9.8 equals our spring constant of 30 times x, which is the stretch distance. Okay, and from there we will get x equals 0.49 meters. All right, so based on this particular spring with the stiffness of the spring, and remember the spring constant is just a constant for that particular spring. The higher the value, the less stretchy or compression that you're going to be able to do with it per unit of force. So 30 is not a very high number for most springs. I mean, they can range from very, very stretchy to extremely stiff springs like what you have on your compression springs in your car. So anyway, so we get to 0.49 meters. All right, let's move on to the next problem. We want to find the gravitational potential energy stored in the Earth spring system before lowering the object. Okay, so if we calculate the gravitational potential stored, so remember, gravitational potential energy is equal to mgh. So we take our 1.5 times 9.8 times h. Now, what we're going to do with this is, remember, these numbers are all arbitrary. So what we will do now is say, at the bottom position here, we can theoretically say that this has a height of 0 meters. Where at the top position now, this is just going to be our stretch distance of our spring. So what we can do is theoretically just say that there's no gravitational potential energy at this point, and all of the gravitational potential energy in the system is at its highest point. So we can just use the stretch distance as the height. When we solve for that, we get 7.2 joules as our energy stored in the spring Earth system at the beginning. Now, when we calculate the actual energy stored in the spring at the bottom, and we set up our equation with our energy of a spring of 1/2 kx squared, where we take 1/2 times 30 times our stretch distance squared, we only get an energy of 3.6 joules instead. So at the unstrained length, the actual energy in the Earth spring system is lower. Okay, so which that leads us to the next question. Why does that happen? Okay, we're forgetting one thing that's in this system right now, and we haven't identified that or taken it into account. In order to lower this, you have to do work on it. Okay, so if we go back to our work energy theorem, remember net work equals a change in kinetic energy. Okay, well the system starts at rest and it finishes at rest. So the change in kinetic energy is 0. Alright, but there are 3 forces total doing work. We have work gravity, plus work done by the spring, plus work done by an applied force. All of these have to sum up to equal 0. Okay, now when we're thinking back, and I know it's been a while since we've just dealt with the work equation, work equals force times distance cosine of theta. So remember, when the force is in the direction of the object moving, of the work done, then the work done is positive. Okay, when the force is in the opposite direction of the object moving, the distance covered, the work done is negative. So if we think about this, the object starts here and moves down. Well, gravity is pointing down, so gravity does positive work on the object. So 7.2 plus. Now, the force from the spring is up though. The object moves from this position to this position, so the work done by the spring is negative. And the applied force, if we're holding this here, is up. If we lower it down, the applied force is still up. So we're moving, or at the bottom, the applied force will end up being 0, but we still have to apply a force up to get it down to this initial position. So the only way to make this equal to 0 is if the work done by the applied force is also negative 3.6. So that is the reason why these two are not equal, is that we're not taking into account the work done by the applied force in this. Okay, I've got 3 minutes here, so let's quickly answer this next one. Now, on this one, we are going to take the work done by the applied force out of the system, and we're not going to just drop it from its unstrained position. Okay, so what we are wanting to do is, this is unstrained, this is at equilibrium, so what's going to happen is, now this thing is going to fall further down. So if we take the work done by the applied force out, that means that only the work done by the spring and work done by gravity is in the equation. At the top position, the object's not moving, so the kinetic energy is 0. At the very bottom position, the object's not moving, so the kinetic energy is 0. So what we can do is just set up a conservation of energy equation and say that the energy stored in the Earth's gravity, or the Earth spring system here, is equal to the energy stored in the spring at this point. So if we derive this equation out, mgh equals 1/2 kx squared on this one. H, remember from the last problem, H is x, because we're saying that the gravitational potential energy is 0 here, and we're saying the spring energy is 0 here. So that means that this H cancels this square out. Essentially, look what happens when we solve for x. X is mg over k, just like we did here, but we move the 1/2 over, and now it's twice that distance. Okay, which makes sense because the work done by the applied force was half of the energy that was used up in the last problem. So now if we go 2 times mg over the spring constant, we get x equals 0.98 meters instead, so the object ends up falling twice the distance as what it was lowered when we did that before. Okay? Alright, that concludes the next one.